Hello, grade 12s. This is going to be hopefully a short little recording on aromatic hydrocarbons. So up until this point, you would have studied alkenes, alkanes, and alkynes. So really what you're studying is the properties of hydrocarbons, which are these big molecules with carbon and hydrogen um, as part of their main structure, and their bonding changes. So we've had alkanes with the carbon-carbon single bond, and from there we saw carbon in the tetrahedral format. We had alkenes with the carbon double bond, and these are where the double bond is. These are trigonal planar carbons because they're AX3. Right? We've got the one carbon attached to the other one and then two other substituents. And then we have the cis and trans isomers of these. And then lastly, you had an alkane, which are linear carbons because they're AX2. So you can start to see the link between the Vesper shape and the actual structure of a larger organic molecule. And remember that each carbon has its own shape in a hydrocarbon, and a lot of the times we'll refer to them as their number, so carbon 1, carbon 2, etc. So now we're going to start to look at aromatic hydrocarbons. We'll look at their properties and how we name them, just like we have been so far. And that's the basis of this unit, looking at how to draw and understand the properties of the compound. So we want to describe the benzene molecule. That's one of our main goals. We want to be able to draw a benzene ring. We want to know what these terms conjugated bonds mean. Those will be very important for the reactivity of this. We'll describe the properties of benzene and then go over some of its traditional names and a specific compound called toluene. So first off, aromatics are a ring structure that contains conjugated or alternating double bonds. Okay, conjugated double bonds are double bonds in a ring structure separated by a single bond. So this is a cyclic hydrocarbon because it forms a ring. So aromatics are not straight chains, they're only ring structures. But you can see here we've got double bond, single bond, double bond, single bond, double bond, single bond. So this alternating pattern, you can see it a little bit better here in the structural diagram, is what's called conjugated double bonds. They alternate and it creates this pattern known as aromaticity. So benzene is the most basic aromatic hydrocarbon, which is why we study it. Everything else builds off of this, but it has the same, they have the similar to the same properties. So C6H6, if you're just given this, you could draw this several ways. You could draw it as an alkene, for example. So we have to have some hint as to what we're drawing before we start looking at it. So that's the main takeaway here, what the conjugated bonding is, and that's what defines the aromatic. All right, it's an older term, aromatic, and these compounds tend to smell pleasant or nice. Doesn't mean they're healthy for us. A lot of this is associated with paint and gasoline. That strong chemical or organic smell is what these molecules all smell like. So the structure of benzene, originally, even though we see that they're alternating double bonds, if we were to measure them, they are not actually different. So this takes us back to our hybrid and resonance structures, which is why you notice the double bonded arrow. So the resonance structures of benzene are called Kekuli structures. Okay, so these are just resonance of benzene specifically. Okay, or aromatic compounds. So this tells us that all the bonds are interchangeable. And if you think back to why we said that, the bond length of a single bond should be longer than the bond length of a double bond, but in practice, when they were measured, they were all the same. So because they're all the same, there must be some hybrid resonance structure forming, and that's what it is. So a lot of times, to represent that, we'll replace the bonds inside the hydrocarbon with a circle. So this circle here, just down at the bottom, if you see that inside of a cyclohexane, that tells you that there's conjugated bonding and that they're all equal. So if we draw this, this is just cyclohexane. This would be cyclohexene. So we've got, just to see the name here. Okay, you can see that the ending changes. Even if we had two double bonds, we called that cyclohexadiene, still not an aromatic hydrocarbon. It has to be conjugated or you have to see that circle. So these are not the same. These are not the same. These are not resonance structures of each other, but these ones are. So that's the unique thing. You'll see either or drawn, so just be able to recognize that alternating pattern. What's really happening here is we have something called electron delocalization. So you want to know this term. It's like what happens in metal ions. So in delocalization, you can see at the bottom here, right, the electrons actually leave the individual atoms and they form like a circuit above and below the plane of the atom. So if we were to draw benzene out, we can see this alternating double bond pattern. Because these carbons are all AX3, this is trigonal planar. So this entire molecule would be flat. It's two-dimensional, not three-dimensional. So if we lay it on its side, floating above and below, these electrons would be racing around. That's delocalization. In a normal bond, they would stick between two atoms. So if this was just a normal single bond, these electrons and these orbitals wouldn't go past these carbons here. But because they've delocalized with this alternating conjugated pattern, they're free to actually cycle. So all the electrons belong to all the atoms of carbon. It's so stabilizing that these benzene molecules are considered unreactive. So even if we take an electron away, it'll balance out the charge from the other five. Instead of becoming -1, it will lose one of the electrons and it will become -5/6 instead. So you can see that it's much lower than that charge. Okay, so that stabilization helps make it unreactive, and we'll notice that for when we get to the reactions. A couple different examples. Benzene's not the only aromatic compound, so we split this into two halves. So all the compounds on the left are conjugated bonding, so they're stable and they're aromatic. Right? Naphthalene, this one here, this is the mothball scent if you've ever smelled that. We've got benzene, naphthalene, anthracene, benzoate pyrene, which is a plastic component. You don't want to see that in your plastics now. We've banned that from a lot of manufacturing. And naphthacene. So as long as the bonding's conjugated, then it's an aromatic compound. On the right, these are not examples of conjugation. So in the first one here, you've got a carbon, a carbon, a carbon. There are two single bonds beside each other. They're not alternating. Here, you've got all single bonds, two double bonds beside each other. That's not alternating. And here, even though this half of the molecule is alternating, this half is not. So the entire structure needs to be alternating for it to be an aromatic compound. In terms of properties, they're very nonpolar, so they're good for dissolving nonpolar substances. Very flammable because they're hydrocarbons. Very carcinogenic, so you can see they're not painting a good picture. These are not healthy molecules for us. They used to be used in dry cleaning because of how nonpolar they are. They would dissolve the dirt very well, but again, they leave behind trace residues and it's very bad for people to be breathing in. They used to decaffeinate coffee beans with them. So to create decaf, they would soak the coffee beans in benzene. It would extract the caffeine because it's also nonpolar. They would rinse them and then crush them out. But they found that the coffee bean would absorb the benzene, so it wouldn't be a safe product over time. Now there's much safer ways of doing that. So the beans are, if you're ever wondering, your decaf coffee is not grown decaf. It has to be treated chemically to remove the caffeine from it. Hopefully that doesn't ruin it for you. They are also found in tars, cigarettes, gasoline. We should update this to vape cartridges. Not directly. Manufacturers don't put benzene in these things like cigarettes and vape cartridges on purpose, but when you burn the organic molecules that are in there, the benzene becomes a byproduct and it gets produced and it stays in the lungs. And then finally, it's unreactive again because we talked about delocalization. So those are the properties. Now let's get to the naming of it. Benzene is the parent chain when there are only smaller groups attached. Okay, non-carbon groups or carbon chains shorter than 5 carbons will be a chain on it. When benzene is the side chain to something that's larger, we write it as phenol. Okay, you can see the name here, and it's considered a side group or a branch, an alkyl group. We'll just write that down there. A couple of other ones, this is where benzene gets a bit confusing, but its name changes based on what it's attached to. So phenol is a benzene molecule. We'll draw a hexagon with a circle, attached as an alkyl group. So that's going to be attached to a carbon chain that's 6 or more. Phenol is a benzene ring with an alcohol attached to it. Benzene is just regular benzene, so that's when it's by itself, or the parent chain. So for example, if we have a chlorine attached to it, or a methyl group attached to it, we use the name benzene as the parent. Benzoyl alcohol will look like this, a benzene with a carbon with an OH, then it's got 2 hydrogens on that carbon there. And lastly, benzoic acid. These are all specific compounds. Will be a carbon double bonded to an oxygen and then single bonded to a hydroxyl group. So make a note of these. The naming is affected by the structure. So let's go through an example. We'll do one of each for these. So if we call these A and B, if I start with A, I always want to go to the end because I see the parent. So I know that I'm drawing a benzene molecule here. The parent chain is always listed last, and that's the longest or the biggest carbon chain that all the branches attach to. So from there, I've got a bromine on 1, a chlorine on carbon 2, and an ethyl group on carbon 4. Now, it doesn't matter where we start numbering. I'll just start from the top. See if I can zoom in here. Okay, and I'll number these clockwise. But again, as long as we're consistent, then we'll be okay. So carbon 1 has a bromine. I'm not going to show the electrons here. I guess I am. Carbon 2 will have a chlorine. Carbon 4 will have an ethyl group, so a bunch of different ways we can draw that. I can do the structural diagram like this just to see what it looks like. Okay, but that's going to get a bit more complicated. And the good thing is we're done. So that's the structure. Or I can simplify that, just simplify the ethyl group at the bottom. So I'll draw a line here and then a line here. Because there's 2 points, 1 and 2, that's the ethyl group. So that would be the full line diagram for molecule A. For molecule B, okay, we can see the cis prefix here, so that means we were working with an isomer. So again, I go to the end of the word, this entire thing, and I've got octene. So let's start with 2 double bonds here. Now I'm not going to draw the entire octene chain, or I guess I can. We'll do this 2 ways. So 1, 2, 3, 4, 5, 6, 7. We've got 1, 2, 3, 4, 5, 6, 7, 8 carbons here. And I'll just number the beginning and the end to keep it organized. The 2 tells me that the double bond is on the second carbon between carbon 2 and 3. So I'll put that right there. On carbons 4 and 6, there are diphenyl groups. So the phenyl or the phenyl group is just a benzene chain, benzene ring on a longer hydrocarbon. So if this is carbon number 1, 2, 3, 4, 5, 6. So there's going to be a phenyl group here and a phenyl group here. So I'll just draw these not to scale. Okay, we've got this little virus-looking structure going on. Okay, so I've drawn the entire compound. Now I just have to check for cis or trans. So when I zoom into that on B, this one that I've drawn here, if I kind of take a look at the double bond, I've got hydrogen up and hydrogen down. Okay, so again, we make an imaginary plane through the double bond. If that's a hydrogen and that's a hydrogen, what I want to do, each carbon has 2 things attached to it. So the first carbon has just a carbon and a hydrogen. So the heaviest one is pointed down, and on the second carbon, I've got a hydrogen on it, and then I've got this massive chain coming off of it. So there are 4 things, again, in a double bond. Each carbon has 2 substituents of the double bond. Okay. In this case, our heaviest substituents are opposite each other. Right? There's a carbon, and again, to go over the heaviest, we look at their molar mass. So because these are opposite, I've actually drawn the trans isomer. Okay, so this is not what the molecule is asking it for us. I need to redraw this so that this molecule has the carbon branches on the same side. So to do that, what I can start with is, I'll start with a double bond, and I'll draw this just facing down. Okay, there is carbon 1 down here, carbon 2, carbon 3, and now I can either go up or down. If I go up, I draw the trans isomer like I just showed. If I go down, now I've got the cis isomer. So I can go 3, 4, 5, 6, 7, 8. And on carbon 4, I'll redraw my phenyl group. This is about as complex as it gets in terms of our drawing. And there's my structure. So this is molecule B, which is cis 2,4,6 diphenyl 2-octene. So again, pause, rewatch that if you need to, because it puts together a lot of different concepts. You might come across these names, ortho, meta, and para. So these are an old naming system. Whenever you see ortho, it just means there are two things, positions 1 and 2. Meta means 1, 3, and para means 1, 4. So if I replace the R group with chlorine, for example, in this example, this would be 1, 2, dichlorobenzene. And if I name it using ortho, I would call this ortho dichlorobenzene. Okay, note the position of the dash and the commas in here. And then this would be 1,3-dichlorobenzene for meta, and para would be 1,4-dichlorobenzene, or just para. You may also see it labeled like this, O-dichlorobenzene. And if it doesn't specify position, just keep them side by side, or keep them one apart if it's 1, 3. So we won't prioritize this, just know that it exists, and you might see it in a few homework questions. Lastly, toluene is a specific example of an aromatic compound. So this is known as methylbenzene. It's a benzene ring with a methyl group on top at carbon 1, and that's it, nothing else. This is paint thinner. So it's a very strong smell, very flammable. It's a runny, non-viscous liquid, and this is used to dissolve old oil-based paints or to get stains off of wood. Unfortunately, it takes the coating off of wood as well because it's another hydrocarbon. And when we start to study this, you'll realize how many things are actually organic compounds that we use. So just know that methylbenzene and toluene are interchangeable names for each other. So that wraps this up. Really go back and look at those examples again if we need to. The homework questions here will do a good job giving you the basics. The thing that you're going to want to focus on is, when do I use benzene and when do I use phenyl? So again, benzene, if there's only short chains like methyl or ethyl groups and chlorines, then we're going to use benzene. If I have long hydrocarbon chains attached to a benzene where it's shorter in length, then it becomes a phenyl group off of the parent carbon. Now there's one exception where if I have a short chain like a butane here with a benzene sticking off of it, although the benzene's longer, if the butane has more things on it, so if it's substituted, okay, we'll call those 2+ substitutions where it's got 2 or more groups on it, then we'll actually, even though it's the longer carbon, we're going to make it the side group so that we can prioritize the branching of the molecule. And we'll talk more about priority later on. So I hope this helps. Good luck with the homework, and be sure to follow up and just keep practicing drawing and recognizing the patterns in the names.